So maybe tell us a little bit about how you first got interested in computer science.
Yeah, I mean, I guess that's sort of a long time ago. I'm from LA. In high school, I was actually very interested in hardware.
Mm-hmm.
I was on the robotics team, but I was doing a lot of different projects um, around a certain problem in India that I really cared about, which was notifying people about water distribution in
Mm-hmm.
villages. And so I manufactured a bunch of sensors, and building the software for that was really, really fun.
Mm-hmm.
I would say back then I was very interested in hardware, but yeah, software was a blast,
Mm-hmm.
and that definitely bloomed at my time at Stanford. Yeah.
Mm-hmm. Yeah, awesome. What specifically made you interested in like sort of computer science for the environment, and sort of what made you want to work with Stephano at the beginning?
Yeah. I mean, Stefan was obviously a really, really amazing researcher, so that
Yeah.
was obvious reason. Yeah, he has a team working on like applications, and I was really, really interested in that. Before that, I was working with Michael Kokenderfer on some other application work, and so it felt like a good transition. So yeah, I spent like a summer working with him, and that was my first paper. Yeah.
Mm-hmm. Cool. All right. So getting into your papers, let's maybe start briefly with one of your papers titled Geo LLM Extracting Geospatial Knowledge from Large Language Models. So you want to maybe give us a brief background on what the paper is, and then we can maybe dive a little bit deeper.
Yeah, so that paper was, the basic thesis was like, well, there's a lot of geographical knowledge in LLMs. Is there a way to make that useful for predictions given like a set of coordinate on Earth? To give you some background, satellite imagery is, for example, one place where people try to make predictions using these images about like many things like population or wealth index and things like this. Um, Language models have basically compressed all of the knowledge on the internet, right? Is
Mm-hmm.
there a way to extract that and make that useful? And yeah, we got very lucky. It ended up working very well.
Mm-hmm. Awesome. So I think in this paper, I think one of the key innovations is this smart prompting strategy where like while LLMs embed a lot of spatial information about locations, just like naively querying LLMs using geographic coordinates isn't effective just by itself. And so instead you need to construct these like rich prompts using like auxiliary map data from OpenStreetMap. Maybe walk us through briefly like some of the results that you had of this paper and how you ended up deciding to, pick the solution of like constructing rich prompts.
Yeah, I mean, the first thing was just like validating if this was even worth pursuing. And
Mm-hmm.
you can do that really easily. Anyone can do that really easily, which is just to like ask it, like, well, given these coordinates, given like, maybe like here's a few different places, like, can you tell me about this location? Is there any useful information? And you'll see like, yeah, they know a lot about locations. There's
Mm-hmm.
just a lot of information on the internet about this. And so they've just soaked this all up. So that's what we first show. The second part is, yeah, like as you mentioned, these rich prompts are definitely necessary to kind of get them to understand what this location is. As nice as it would be to just give them coordinates and then have like an amazing prediction, they don't have like a good understanding of coordinates. Maybe in the future they will. Who knows?
Mm-hmm.
But yeah, giving them like being able to like triangulate exactly where something is and giving them names and locations of things that might have more relevance was very important in getting like the best performance out of the models. Yeah, and the second part was like, yeah, fine tuning definitely helps. It definitely just gets the model to learn that distribution better, and it kind of unlocks a lot of the information that otherwise would have been a little bit harder to get.
Mm-hmm. Yeah, I think one of the interesting results is this concept of model scaling, where you see that like GPT 3.5 outperformed Llama 2 and Roberta in the paper by like 19% and 51%, respectively. And so that sort of shows us that like performance of the method sort of scales well with the size of the model and its pre-training data set. Want to maybe walk us through a little bit of some of the scaling results that you saw from this paper and maybe some of the intuitions that you had there?
Yeah, I mean, to be honest, I don't remember the exact results, but
Yeah.
basically, yeah, it was really exciting to see. Like, we tried this, or I tried this first on Roberta, which is like
Mm-hmm.
a newer version of BERT from Facebook,
Yeah.
and that ended up working pretty well, and that was very exciting. But then, Llama came out at the time,
Mm-hmm.
and we tried it out on that, and it worked even better.
Mm-hmm.
Even though the training dynamic was really weird at the time. It was like, okay, well, it spits out text. That's kind of weird for a regression problem,
Mm-hmm.
but it ended up working better. And so that was a clear indication that it matters way more what's in the model as opposed to like the architecture.
Mm-hmm.
And then, later in the paper, like GPT 3.5 came out, or like the fine tuning for that model came out.
Mm-hmm.
And then when we fine tuned that, it worked like way better than Llama. And so there was
Mm-hmm.
clearly scaling that was helping here, like the size of the model as well as the pre-training data set. So yeah, that was looking very good. Just like over time, this will just get better,
Mm-hmm.
Yeah.
Yeah, for sure. I think one thing that's interesting about the technical approach is that you guys, like, as opposed to using a regression, you guys use classification with 100 bins, where you guys sort of split bins from zero point 0.0 all the way up to 9.9. And apparently that particular technique works better with LLM's token generation process. If you want to explain briefly why you guys chose to use classification instead of regression here.
Yeah, so I mean, like one approach you could use is like, well, let's stick a head on this model, and a regression head on this model, basically change the architecture. That is very valid, and that is what we did for Roberta. But you want your predictions or your task to be as in distribution as possible, meaning like it has to be natural to what the model has already learned to do. And by putting it in this sort of like textual form, it already has a good prior as to what this task is, and
Mm-hmm.
you can take advantage of that prior a lot better. And so you can end up like getting better predictions, especially when you have like a lower number of samples.
Mm-hmm.
Whereas like if you added a head, it might take quite a bit more samples to like get it to learn how to do that.
Mm-hmm. Cool. I think one other aspect of this paper that's really exciting and pretty significant is that, as opposed to having to do things, where you're looking at like satellite-based methods, in order to get, geospatial analysis, this is like super valuable for things like international development, urban planning, policymaking, because these LLMs have substantial geospatial knowledge and you can sort of extract it from the LLMs. So I mean, obviously geospatial data is like one potential, application here. Like what are some of the other potential applications where you can sort of extract data from LLMs?
I mean, I'm sure there's plenty of applications. I mean,
Yeah.
off the top of my head, you know, yeah, I guess like I mean, yeah, I guess like, using these as like search engines has been like
Mm-hmm.
really amazing, right? Like they've compressed all the knowledge and it's like very accessible if you
Mm-hmm.
fine tune them in the right way. I mean, everyone knows this now,
Yeah.
but that's like an obvious thing. And yeah, any application that really requires about that last like 20% of performance, yeah,
Mm-hmm.
that's where you need to like engineer your like prompts. That's where you need to start fine tuning. That's where you need to think about the way that you train it and that kind of thing.
Mm-hmm.
Uh, but yeah, we've obviously seen knowledge is like a big application of LLMs. Yeah.
Mm-hmm. Yeah. Awesome. So maybe now we can move into one of your other papers that was really exciting. So you worked on a paper titled Large Language Models Are Geographically Biased, which is sort of like a follow-up to the paper that we just talked about. Do you want to maybe briefly give us an intro into this one and then we can dig a little bit deeper?
Yeah, so this was like an obvious follow-up to the last paper, right? We established a way to pretty reliably extract information out of the LLMs for specifically like given a coordinate. And so like a very, interesting question was like, well, how do they do? Especially when you don't fine tune the model. If you don't fine tune the model, like what does it believe the sort of like world looks like with different, aspects like population or wealth index or maybe even subjective topics. And so yeah, we introduced a way to kind of do this in a zero shot manner, so without any training. And then, an aspect of this was basically like this could be used to evaluate the model, right? We have like ground truth for a lot of these different things, so we can literally just compare like the correlation between the predictions and the ground truth, and that will tell us how much it knows. But another kind of very interesting aspect and kind of what we really focused on was was bias, especially on more subjective topics, you know, subjective sensitive topics where it might not be a good idea to show an opinion, right? For example, like attractiveness or like morality or you know, intelligence, like, you know, especially for LLMs where, you know, like the company cares about like what the model says, right?
Mm-hmm.
And so um, yeah, it can be used like as an evaluation for that, where like the ground truth can just be like, well, we want it to say kind of the same thing for every place. And here, this like the biggest kind of observation we found, or like significant finding, was like for these subjective sensitive topics like morality, intelligence, attractiveness, you know, these kinds of things, it showed a very consistent bias that was predictable across like almost every topic, which was that it was basically just biased towards wealth.
Mm-hmm.
If that location doesn't, it has a lower wealth, you know, GDP per capita, it's like very likely to have a lower average prediction from the model. And this was very, very consistent across many models and across many topics. You know, it's like, for example, like especially like all of Africa was basically like always rated lower. And you know, that's yeah, that's that can be a problem, right?
Mm-hmm.
You know, when people are post training their models, they might want to take that into account, that, you know, the model definitely has like priors that maybe you don't want to show when you ship a model. Um, yeah, I guess that was kind of the core thing there.
Yeah, awesome. I think there's these sort of like two different threads that I found interesting about the paper. Like one is like, you are able to show that LLMs are capable of making accurate zero-shot geospatial predictions in the form of ratings, and you are also able to show this like strong monotonic correlation with the ground truth. And then you're also able to show like kind of along with that thread, the fact that when you have these prompts where you give them like geographic coordinate or you give them address or you give them nearby places, the LLMs can actually accurately predict these objective measures. So that's like one thing that I found interesting about the paper. And the other thing I found interesting about the paper is like just like you were sort of outlining, right? There's these ideas of geographic biases where like that capability also sort of allows these accurate predictions to have the systematic bias. So I guess like maybe one question I have here is like, you have these LMs, you're sort of claiming that they can accurately predict these objective measures, but then you're also saying that there's some bias. So I guess is the bias in the objective measures, is the bias not in the objective measures? Like, is it more in the subjective measures? Like, where is sort of like this delineation between this accuracy and making these objective predictions and then this bias?
Yeah, I mean, like the biases were definitely both in the objective and the subjective topics. It wasn't just subjective topics.
Yeah.
Yeah, like especially for example, for you know, we had ground truth data on like infrastructure, for
Mm-hmm.
example, and it definitely kind of like stereotyped like, oh, like I don't know, uh, South Asia has like very little infrastructure, when even though it actually had a bit more infrastructure than it predicted.
Mm-hmm.
So there were definitely a lot of biases, like even on objective topics. So yeah, I would say like the sensitive subjective topics were kind of like the oh my gosh kind of things, but
Mm-hmm.
then yeah, it applies kind of just everywhere,
Mm-hmm.
pretty much. Yeah.
Cool. And you guys also introduced this bias score that incorporates like correlation. Like for example, like you have some anchoring distributions, like maybe infant mortality. You guys also incorporate mean absolute deviation of ratings, so like how much the ratings are vary. You guys also incorporate like answer rate, like how often the model refuses to answer. And then in your model comparison results, you were able to show this concept of like there's this significant variation in the magnitude of bias across existing LLMs. Like for example, GPT-4 Turbo and Llama 2 70B are the least biased ones. Maybe like Gemini Pro is the most biased one. Maybe talk to us briefly about like how you came up with this bias score thing, and then also like how you went about sort of comparing different models.
Yeah. I mean, I guess the bias score was kind of, it was specifically designed for the subjective sensitive
Mm-hmm.
topics. But yeah, it also kind of generalizes to any other topic. But
Mm-hmm.
yeah, it's like kind of, you know, how correct is this? You know, we kind of assume that there is a correct distribution, and basically you measure the sort of deviation away from that. And as well as like, we also give an opportunity for the model to just say like, well, I don't want to answer this, because maybe that's actually the better, you know, answer in in that scenario. So we also took into account that in the in the score. Yeah, I mean, at the time, it was pretty clear, like, some people had put a lot of time into post training the model to like be like kind of as unbiased as possible, and that showed like with OpenAI's models, for example.
Mm-hmm.
Some other models definitely seemed like they needed some work, but that was back way back. Like these companies have definitely probably figured that out quite a bit more now. Um, yeah, yeah, but back then there were some clear like large variances in the scores between these models. Yeah.
Hmm. Yeah, I think another thing that was interesting is you guys also introduced this concept of like high resolution bias detection, where you're like able to detect bias at these like very granular levels, like neighborhoods of the same city. You're able to show these like systematic rating differences between different types of socioeconomic conditions. Maybe talk to us briefly about like the concept of this high resolution bias detection. Like, is it like categorically different than some of the other sort of bias metrics that you came up with? How does it sort of different or differ from this geographic bias framework?
Yeah, I mean that is actually pretty much exactly the same.
Mm-hmm.
It's just yeah, it's more granular.
Yeah.
Like, we could basically got like a bunch of prompts in say like the Bay Area,
Mm-hmm.
and you can clearly see there is correlation with wealth
Mm-hmm.
in and basically the same exact findings apply,
Mm-hmm.
and the same exact metrics you can use to measure that. So
Mm-hmm.
yeah, it's just like basically it's agnostic to like the resolution that you apply it to.
Mm-hmm. Awesome. All right, let's get into your third paper. Really exciting paper. Adaptive inference time compute. LLMs can predict if they can do better even mid-generation. Maybe you want to give us a brief background in this one as well.
Yeah, so this paper is really trying to basically make like these methods like best of n, best of n being like you generate multiple samples or like multiple responses from your model, and then you try to pick the best one. Um, Basically making that a lot more efficient, and basically it does it in two ways. One is that you avoid having to use an external reward model to pick the best sample, and then second is we you can adaptively allocate the compute by basically trying to get like is it worth using more compute or not. And the actual implementation basically is like, well, what if we could prompt the model at any point in its generation, and get its prediction for the probability that restarting generation will yield a better outcome.
Mm-hmm.
So you can imagine, like in the middle of the generation, you can just ask it, like, should we start over? And if it says yes, then maybe you should start over. Or at the end of the response, like maybe you think it can do better, then you can know if it can do better, and then you can sample more times and then do best of n.
Mm-hmm.
Um, so yeah, just trying to make it as efficient as possible. And so you can do like pruning, you can do like adaptive sampling.
Mm-hmm.
Yeah.
Mm-hmm. Awesome. So yeah, as you sort of mentioned, there's these two key techniques that you guys present in the paper. This first one's like adaptive sampling, so you can like generate a bunch of additional samples only when the model predicts improvements likely. And then the second one's like this concept of early pruning, where you can like stop generating unpromising samples mid-generation. Do you want to maybe talk to us briefly about like sort of why you picked those two as the two main techniques for this paper? Maybe any like trade-offs with the two different techniques, and maybe sort of benefits of having both of them.
Yeah. I mean, so the main distinction between these two is like one, you have to do the adaptive sampling basically is saying like, all right, I'm going to do one sample. I'm going to see if doing another sample is worth it.
Mm-hmm.
I do another sample. And you keep doing this. The Basically it's like you have to do that in series. So if you care about time, right? If you care about wall clock time, for example, that's maybe not the best way to go about it.
Mm-hmm.
And in that case, like pruning actually makes more sense. And what I mean by pruning is I'm saying like you're gonna do say like 8 samples, but like midway through the generation, you can like prune, I don't know, whatever, 75% of the samples and
Mm-hmm.
then keep generating the top 25%. And in that case, like your wall clock time will be pretty good.
Mm-hmm. Yeah, maybe walk us through how you sort of went about constructing the training data set. I think you guys had a pretty interesting approach. You guys had this on policy preference data set where you used responses from the same model being trained and scored by this thing RM, which is trained on 1 million preferences. And then you guys had this insight that I thought was really interesting where you show that like approximately 40% of the ties are in the preference data set, which is essential for learning when the model cannot improve. And so you guys sort of had this data set structure. If I'm not mistaken, you had like this good responses, bad responses, and like this crucial addition. Like maybe walk us through like how you decided to have that structure for the data set.
Yeah, that's a good question. I mean, yeah, this is definitely, kind of like an empirical, like a part of the method that came out of like empirical observation, which is just like a lot of the responses are kind of the same, and it's hard to say if it's actually better or not. And so that's why we introduce like these things like ties, basically, right? So, like the way that this data set is constructed is that you get two responses from your model given every prompt, and you're basically seeing like does one sample win over the other, or is it just a tie? Are they just like really similar and it's like there's barely any distinction?
Mm-hmm.
Um, so yeah, that happens a lot of the time. But the case that we actually care about is when one sample is significantly better than the other.
Mm-hmm.
Basically, what we actually care about is like the probability that you can do better.
Mm-hmm.
If you can't do better, then we don't care.
Mm-hmm.
This is just a sample you're going to use.
Mm-hmm.
Yeah.
Great. So I think another thing that's interesting is like your experimental validation. So you guys are able to demonstrate a few different performance gains. You show that like for alpaca eval, for instance, like the win rate against GPT-4 increases from 21% to 34%. And then you guys also have this other result where you look at the GSM 8K, which we talked briefly about, where performance improved from 84 to 91%. And then you also have the scaling effect that you guys also discussed, where you show that like Llama 3.18 billion approaches Llama 3.170 billion performance. Like maybe walk us through some of those validation performance gains, any results that you thought were interesting or particularly exciting.
Yeah. I mean, yeah. So, test time scaling or like basically doing more samples just gets you better performance.
Mm-hmm.
And you can kind of measure that against performance gains in larger models, right? Larger models are obviously better. And so you can kind of compare these like orthogonal directions of scaling compute. And so, yeah, that's why you can compare against the 7DB model. Um, yeah, I guess like what was really nice about this method, especially like I think on the adaptive sampling side, was just that you can really get to the point where the performance with this scaling saturating like very quickly. Like you can get to that top performance just a lot quicker than you would have otherwise,
Mm-hmm.
right? With less total samples.
Mm-hmm.
Which was kind of the goal, right? Like we're trying to make it adaptive. We're trying to allocate compute only when it's actually necessary
Mm-hmm.
instead of just all the time.
Yeah, speaking of the sort of this adaptive concept, I think you guys also ran this efficiency analysis in the paper where you had this adaptive threshold, which we can say, for example, called tau, that provides this fine grained control. And when you set tau to like 0.92, you get some amount of max improvement, some number of average samples. And it's sort of like one trend that I saw is, as you increase tau from like 0.92 to say, for instance, 0.99, you see that, max improvement increases from say 73.5% to 97.1%, and the number of average samples increases from 1.2 to 6.8. Maybe walk us through briefly like how you ended up choosing those values of tau to test, we see this trend, like what's the intuition behind it.
Yeah, I mean, yeah, those values are basically like the kind of sweet spot at which like you can kind of see the performance go from like, or you can see that the compute allocated is like sort of analogous to different best of ends. So like best of two, best of four, best of eight, best of 16, right? Those taus basically allow you to allocate that much compute respectively. So basically it's like if, with tau in the limit, it's like it'll just be best of 16, and there's no difference between best of 16 and the method. With different taus, you kind of get the effective compute of like best of two, best of four, etc. But because it's more adaptive, you get a higher effective like performance at those levels of compute. Yeah.
And in terms of like thinking about some of the advantages of this over some of the other approaches, like maybe I'd say like the two main traditional approaches I can see here are like the external reward models approach and just as you sort of highlighted earlier, the simple best of n approach. So like maybe one potential benefit I can see of this approach over the external reward models is there's no additional memory and storage requirements, and you can also have this like KV cache reuse versus simple best of n. You sort of have this concept of adaptive allocation, which means you can sort of determine the number of samples you need, where you can have more for hard problems or fewer ones for easy ones, and you also have early stopping. Are there any other advantages you might want to like highlight over some of the existing approaches?
Yeah, I mean, honestly, the biggest one is just that it's adaptive,
Mm-hmm.
right? That was just kind of lacking in pretty much all the literature.
Mm-hmm.
And many of the times, right, like one response is going to be good enough, right?
Yep.
And we see this, in like, for example, like ChatGPT nowadays, right? They have like a router to like different modes of ChatGPT. Like, what if the model itself can just figure this all out, right?
Mm-hmm.
Like, people speculate that the pro version is like some combination of like parallel sampling and like
Mm-hmm.
long reasoning and these kinds of things.
Mm-hmm.
Getting the model to like figure it out on its own is pretty important.
Mm-hmm.
Yeah, I would say like, I'm working on kind of like follow-up work on this
Mm-hmm.
where really trying to hit wall clock time.
Mm-hmm.
Basically, this method we were trying to do pruning, but that pruning was definitely, not super robust, right? Like we were
Mm-hmm.
kind of just doing pruning like 75% of the samples at one point in the generation. Yeah, there are definitely many better ways to do it,
Mm-hmm.
to hit like basically like much higher performance at the same wall clock time.
Mm-hmm.
Um, so yeah, this is definitely there's many ways to improve over this, but the kind of main takeaways here is like, well, it can be adaptive. You don't want to only stick to the absolute reward,
Mm-hmm.
and to like the same model can do it and they can do it mid generation. I would say are like the main takeaways.
Mm-hmm.
Yeah.
Yeah, and I guess like beyond the takeaways, there's also this concept of like limitations and maybe future work. I think one of the limitations you guys talked about in this paper is how like adaptive sampling could potentially introduce latency, and then that could otherwise maybe not be a problem with just parallel sampling. And you guys also sort of talked about how you might mitigate this using like exponential batching, and then I think also briefly in like the future results section, you guys talked about how you guys could theoretically explore like beam search or some other structured search algorithms that could leverage capability aware evaluations. Maybe walk us through briefly like what are the main limitations you think that adaptive sampling has? Like which one of these like future work directions do you think sounds sort of the most appealing and why?
Yeah, I mean, honestly, the biggest kind of bottleneck with this method is just the way that it's kind of engineered,
Mm-hmm.
in that the way that you get the prediction from the model is by prompting the model
Mm-hmm.
in the middle of the generation.
Mm-hmm.
And that is kind of just pretty inconvenient from an engineering perspective. So a lot of what I would say unlocks many of these things that we mentioned
Mm-hmm.
is like doing it without having to prompt the model.
Mm-hmm.
Like the model just does it in real time.
Mm-hmm.
Um, so yeah, that would be the main thing. And then of course, like right now, it's kind of it's limited to telling you the probability that one more sample is better.
Mm-hmm.
It will give you a better outcome, but it doesn't tell you like, well, what if you wanted to do 8 of them for
Mm-hmm.
something?
Mm-hmm.
So yeah, I would say those are the main two things.
Mm-hmm. Okay, totally makes sense. All right, let's switch gears now into talking maybe a little bit more about your industrial presence. So, maybe like a few years ago, you were at Meta doing some software engineering things, and now you're also sort of a researcher at Liquid. Maybe sort of, walk us through this sort of different aspect, which is like, we have Rohin Manvi, he's like an undergrad at Stanford, he's doing research, but also, wants to get experience in industry. Like, how do you sort of, straddle these like two different worlds of like potentially becoming a software engineer after graduating, getting a PhD, choosing what to do with the context of like a lot of the listeners, a lot of them will be grad students, but some of them might be like really, really exceptional undergrads that are working on research. Like, what would you say is like maybe some of your experiences on the industrial side that you think might be relevant for them to have context on?
Yeah, this is a good question. I mean, just to give a little bit of background, I did internships at Meta and a startup called Lacework, doing software engineering, and both of those internships were actually before I was like involved in research at all.
Mm-hmm.
So I was very interested in software engineering. Actually, a friend of mine and I even started like a boot camp to get people full-time jobs, and we
Mm-hmm.
were very interested in this. software engineering and that whole pipeline.
Mm-hmm.
Um, yeah, I would say that was really fun. I liked, I definitely like software engineering. But I guess the thing that I felt was kind of missing was like, well, some of these problems are maybe not as interesting as I'd like. And, working on research just felt exhilarating,
Mm-hmm.
even if things don't work, it was just like, it was really, really fun.
Mm-hmm.
And that's what I found out. I definitely found out a little bit later in my time at Stanford.
Mm-hmm.
And so I would just say, like, yeah, don't be discouraged if you're a little bit late to the game.
Mm-hmm.
As long as you really put, the pedal to the metal and you get a few papers out, you'll be fine for, like, say, things like PhD admissions, or if you want to do research at some company, just as long as you do it, it doesn't really matter when you start.
Mm-hmm.
Um, yeah, honestly, research in academia and research in industry, that they're honestly like not as different as you would think. Like a lot of it just comes down to like velocity and just how fast can you do things, like how
Mm-hmm.
many things can you try.
Mm-hmm.
And that also just comes down to how well you can execute your ideas, and not get into like bottlenecks and pitfalls and things like that. So yeah, it's not that different. I think it's more just like, what do you want to do and what are you excited about?